At this point in Chapter 10, we've learned two things. First, we've learned how to develop a Taylor or Maclaurin polynomial of finite degree to approximate an elementary function on a small interval. In the last video, we took that a step further and looked at our second skill, that is generating a Taylor and Maclaurin series, which is ultimately a polynomial of infinite degree. The intent there was to replace an elementary function with a Taylor or Maclaurin series. The conclusion that you can draw from that analysis is that any elementary function can be replaced with a polynomial function. That is a polynomial function of infinite degree. So we can use Taylor and Maclaurin series to replace any elementary function with a polynomial function. So why would we want to do that? Well, think about your experience with integration at the beginning of this class. We looked at some problems that were pretty difficult to integrate, although we were able to manipulate those abstractly at least and figure out the antiderivative. There are some integrals that exist for which none of the methods that we learned in this class will actually execute the integral. That sounds a little depressing, but the window of opportunity here is that if we have an integrand that is difficult or impossible to integrate analytically, that is using processes that we've learned, we can replace that integrand with its equivalent Taylor or Maclaurin series, right? We can replace a complicated function with a polynomial function. Now, polynomials are very easy to differentiate and integrate. So if we can replace a complicated or a tricky function with their power series equivalent, then we can execute the operation, whether it be integration or differentiation. Then we could make an attempt to convert the resulting power series back to an elementary function. This is one method that you'll learn in differential equations for solving very difficult differential equations that have non-constant coefficients. You'll replace those functions with their equivalent power series, solve the differential equation, and then convert back to elementary functions. In fact, your calculator uses this very technique to evaluate trig functions. For example, when you type in sine of 45 degrees, it's not actually utilizing a sine function. It's using an underlying program with the equivalent Taylor polynomial. It evaluates that trig function under a certain amount of error and then yields the result on your screen. And this carries us into a branch of mathematics called numerical analysis. That class may be in your very near future, where you learn how to evaluate integrals and derivatives numerically, that is with these numerical processes, replacing elementary analytic functions with Taylor series and Maclaurin series and doing your analysis from there. So the result of this is that we have some common functions where we conveniently and often replace them with their power series equivalent. So you see a list of these common power series below. I want to draw your attention to a couple of these. One is cosine of x. So the elementary function is cosine of x. You can see the expansion of the power series or the development of the polynomial, and then you can see this power series expressed with summation notation. Now, if that looks familiar, well, that's good because you generated that on your own, or at least together with me in example 5, right? We had an elementary function, cosine of x. We found the first 4 non-zero terms, and from that pattern, we were able to induce the general form for the Taylor series. So notice we have -1 to the k, x to the 2k over 2k factorial. And that's exactly what we have down here. This is the same formula that we were able to generate. In addition, look at this formula, e to the x. E to the x expands into a polynomial like so, and here's the representation of that polynomial in summation notation. Even though we didn't do e to the x, we did look at e to the negative x on example 6 in the previous video. And we were able to generate the power series using summation notation. Now the difference between these two, the one we did was e to the negative x. So if we come down here and manipulate this formula and replace that x with negative x, then we could replace all of the x's in this formula with negative x's as well. Notice if we replace the x's with negative x's, it would generate an alternating series. And that's exactly what we came up with. We had an alternating series, which is indicated here by this -1 to the k term. There was one additional difference on example 6 from the formula that we're considering. Example 6 was centered at natural log of 3. The formula that you see listed here is a Maclaurin series. It's centered at x equals 0. But if we were to replace x with x minus natural log of 3, that would shift that Maclaurin series over to become a Taylor series. So these common representations are very likely to show up in your differential equations class. That is, you'll have an elementary function and you'll replace it with its equivalent power series, or vice versa. You may have an expanded polynomial like this, and it will be your job to associate it with an elementary function. So one fundamental skill that you'll need to know is how do you take these basic elementary functions and manipulate them to match similar functions with different details. So on example 7, we want to know what is the power series representation of f of x equals hyperbolic cosine of 2x. Well, in our formula list, we have the expansion of hyperbolic cosine of 1x. And we want to figure out what's the expansion for hyperbolic cosine of 2x. So what we're going to do is replace the x's with 2x, right? Or if I look at my summation notation here, I'm going to replace that x with 2x. So we could say the series is from 0 to infinity of 2x to the 2k over 2k factorial. Simple as that. So you have the power series representation of hyperbolic cosine of 2x. Again, that simply means that I can replace hyperbolic cosine of 2x with its corresponding polynomial of infinite degree. I can analyze that polynomial under integration, differentiation, in the context of a differential equation, and then convert it back to its original function. So in this fundamental list of formulas, they are very basic, but it gives you the option and the opportunity, the potential to represent a lot of different elementary functions conveniently in terms of these power series expansions, just by manipulating the basic functions like we did on our last example 7 here. So that completes our chapter 9 and 10 studies. I hope you found that last part profound and interesting, that every single elementary function has some sort of polynomial equivalent, though it may require a polynomial of infinite degree. To me, that's mind-boggling and very interesting. So I hope that you are fascinated by that and that your intellect is stimulated by thinking about that. Okay, you are ready to proceed after a little bit of study and finishing up homework. You are ready to proceed to the exam. So good luck on this exam.